neighboring coil. Okay, so few points you have to remember. Few points you have to remember. So this is a solenoid. If this solenoid have the current I, then magnetic field in the solenoid is given by mu naught n I. Mu naught is the relative permeability. Small n is the number of turns in the solenoid per unit length of the solenoid. I is the current in the solenoid. And one more formula you should know. Magnetic flux. Magnetic flux is given by BA cos theta. What is B? B is the magnetic field linked with any coil. Okay. And A is the area of the coil, and theta is the angle between the magnetic field vector and area vector. Magnetic field vector and area vector. So this is the construction of transformer. This is the construction of the transformer. So we will see what are the main components of the transformer. What are the main components of the transformer? See this first white part. This white part. This rectangular white part. One is this, and here is one another rectangular white part. This is basically like this. You can imagine like this. This is one part is this, and another part is this. Another part is this, like this. Okay, this white part, and this is like this. And here are the number of turns of here are the number of turns of wire, and this is known as the winding. This yellow color is the wiring. This is yellow color. This yellow color is a wiring, and this wiring is known as the winding. Here also there is a wire I have shown with yellow color. This is known as the winding. So basically this winding is connected with an AC source. This is a symbol of AC source, and here is another winding connected with an AC source. Okay. So these are the turns. These are the turns. Suppose there are some turns here in this coil. There are turns in this coil, and there are some turns in this coil. So basically, this is the primary coil. So I am considering this as a primary coil. So NP is the number of turns of the wire in the primary coil, and NS is the number of turns. NS is the number of turns of wiring in the secondary coil. This is the secondary coil basically. This is the secondary coil, and this is the primary coil. This primary coil is connected with an AC source. So here I have written input voltage. Input voltage means this voltage is alternating voltage. So here an AC source is connected. Means you are providing some input voltage to this primary coil. Here is this is the secondary coil. The secondary coil is also connected with an alternating voltage. So here we will get the output voltage. Means we will get we will give transformer some input voltage. That voltage we will give. Suppose if we want to reduce the voltage, then we will if we want to reduce the high voltage, so at input we will give the high voltage, then automatically due to some phenomena that I will explain you, due to that phenomena, that high voltage here will be converted here to the low voltage. Okay. So this is the primary coil, secondary coil. NP is the number of turns in the primary coil. NS number of turns in the secondary coil. And basically this white color thing is a soft iron core. White color thing is a soft iron core. Soft iron core. Okay. Now you will say, sir, what is this blue color thing? This is like blue color thing. What is this? Basically, uh, see this yellow color winding. See this yellow color winding. If you are observing this yellow color winding and this yellow color winding have some input voltage, means this yellow color winding will have the current. Okay, now see here. What happens when the winding have the current? There is a magnetic field, and I have told you that magnetic field is axial. That magnetic field will be axial, or you can say magnetic field lines will be axial. Okay, so due to this winding, in this winding the current is there due to this voltage, so there will be these magnetic field lines. These are the magnetic field lines. Basically, these are the magnetic field lines, and these magnetic field lines are axial. These are the magnetic field lines. Okay, this thing I think clear. Okay, so we know that this is the alternating source. This is the alternating voltage source, or you can say this will provide this winding an alternating current. And I have told you alternating current is changing with time, means in this coil the current is changing. If the current in the coil is changing, then the magnetic field in the coil is changing. If the magnetic field is changing, so you can see here what is happening. See the whole phenomena, what is happening here. These are the magnetic field lines due to this coil. As this is a soft iron core, na, so this soft iron core will try to give these magnetic field line to this coil, basically this soft iron core has a property to attract the magnetic field line. So due to this soft iron core, the magnetic field line will follow a path like this. Magnetic field lines are generated in the primary coil. From this primary coil, the magnetic field line will go like this, and finally the magnetic field line will be across the secondary coil. Now here the magnetic field is changing. So here the magnetic field is changing now. So this magnetic field is linked with this coil also. So you can say here also the magnetic field is changing. Now magnetic field is changing here. You have supplied the you are changing the current here, not you. Current is changing in the primary coil. Magnetic field is changing here. What happens when the magnetic field change from this formula? If the magnetic field will change, then you can say the magnetic flux linked with the coil will change. So here finally you can say that magnetic field is changing here. Then you can say that magnetic flux linked with the secondary coil is changing. Now finally conclusion, current is changing in this coil, then magnetic flux in this coil is changing. Okay, now according to the Faraday law of electromagnetic induction, whenever there is a change in the magnetic flux linked with the coil, EMF will be induced in that coil. So in this coil, the magnetic flux is changing, magnetic flux linked with the coil is changing. Then we can say there will be an induced EMF in that coil, and that induced EMF will be the output. And that will be changed by the number of turns of the coil accordingly. Okay, so one by one I will explain. So basically 5b I have written this magnetic flux linked with this coil is changing, and magnetic flux linked with this coil is given by B dot A, or you can write BA cos theta. You can write BA cos theta. BA cos theta you can write. What is theta? Theta is the angle between the magnetic field vector and the area vector. Now, so magnetic field is changing. Remember that the number of magnetic field lines here and the number of magnetic field lines here are same. Okay. See here, 3 magnetic field lines here, 3 magnetic field lines here. So we can say the magnetic flux linked with primary coil is equal to the magnetic flux linked with the secondary coil. So we can say magnetic flux linked with each turn of primary coil of primary coil is equal to the magnetic flux linked with each turn of secondary coil. That is given by phi. Basically, phi is the magnetic flux linked with the primary and the secondary coil. Okay. So basically, this is the magnetic flux. This is the magnetic flux linked with each turn of the coil. Means for one turn of the coil, not for all turn of the coil. So for primary coil, if I say for primary coil, how many number of turns for primary coil? N suffix p are the number of turns for the primary. If I want to calculate the total flux for the primary coil, that will be given by number of turns in the primary coil into 5. Okay, so 5p is given by number of turns in the primary coil. What is 5? 5 is VA cos theta. Okay, so no problem. VA cos theta, no problem. Now for secondary coil, I can write for secondary coil this total flux linked with the secondary coil is equal to ns into 5. I can write this. Okay. Okay. We know the Faraday law of electromagnetic induction. EMF induced is given by minus d phi by dt. Many times I have used, many times, hundred of times I have used. So this is a flux in the primary coil, and this flux is changing with time because the current is changing. So if I want to calculate the induced EMF, in primary coil, that is induced EMF in primary coil is given by minus of d of phi p by dt. Okay, d of phi p by dt. And what is phi p? This is d by dt of Phi p is np into phi, np into phi. So we can write this will become minus of np into d phi p by dt, d phi p by dt. Okay. If I want to calculate the induced EMF in secondary coil, induced EMF in secondary coil, that is E suffix s is given by minus d phi s by dt minus d by dt of ns into phi. This will become minus of ns d phi by dt, d phi s by dt. And uh, we know that basically this is phi p here. What is phi p? Phi p is np into phi, np into phi. Okay. What is phi s? Phi s is ns into phi. Phi s is phi s is see phi s is ns into phi, ns into phi. So in secondary coil, the EMF induced will be minus ns by d minus ns multiplied by d phi by dt. So in primary, the induced EMF will be minus of np d phi by dt. In secondary, this is n secondary d phi by dt. Suppose this is your equation number 1. Suppose this is your equation number 2. Okay, so divide equation 2 by 1. Divide equation 2 by 1. What you will get? You will get ES divided by EP is equal to, you will get NS divided by NP. Why? Because this is ES by EP and this d phi by dt and d phi by dt will be cancel out. This minus sign and minus sign will be cancel out. So this will you get. What is ES? Induced EMF in secondary coil. What is EP? Induced EMF in primary coil. What is ES? I have already written, so we will not waste time. Okay, write down first this, then we will discuss further. I think uh, you have already written this, huh? So, Nida, yesterday have you completed this? And Hamza? Okay. So now write down from here. Hamza, take the screenshots. Done. Okay. Okay. So after this, this is completed. Okay. Now this relation, remember this relation. What is this? In case of transformer, remember this relation. Now, if secondary voltage if ES is greater than EP, okay, secondary voltage means, see here, output voltage means finally you are getting high voltage. You are getting a high voltage finally. Means, Nida, tell me, if secondary voltage is greater, then will it be a step up transformer or step down transformer? Finally, we are getting high voltage. Step up. Very good. Step up. So means this will be a case of transformer, step up transformer. So in step up transformer, you can write here step up transformer. Secondary voltage or output voltage is greater than the primary voltage. So from this equation, if this ES by EP is greater, then you can say this NS by NP will be greater than 1. I want to say that if this EC is greater than EP, so this ratio will be greater than 1. If this ratio will be greater than 1, then this ratio will be greater than 1. So you can say that NS divided by NP greater than 1. So number of turns in the secondary coil must be greater than the number of turns in the primary coil. So you can write number of turns in the secondary coil will be greater than the number of turns in the primary coil. So this is the condition for the step up transformer. For the step down transformer, number of turns in the secondary will be lesser than the number, no, induced EMF in the secondary will be lesser than the induced EMF in primary. Number of turns in secondary will be lesser than the number of turns in primary. So you can identify the type of the transformer. If on the side of the primary coil number of turns are less, if on the side of the primary transformer, if on the side of primary coil of transformer, if number of turns are less, then which type of transformer will it be, Hamza? Can you tell me? I am saying on the side of primary coil, if the number of turns are less than the secondary, then which type of transformer will it be, step up or step down? Step up or step down? Nida? Okay, Nida, you tell. I have already written this. This will be the step up transformer. Number of turns in secondary is greater than number of turns in primary. Okay. So after this, I am just considering that this transformer have the 100% efficiency. 100% efficiency means there are no losses. Means we are supplying the energy here, and here we are getting the same amount of energy. Here we are supplying the electrical energy, same amount of electrical energy we are getting here. I am assuming that the transformer is 100% efficient. 100. But remember, in this world nothing can be 100% efficient. So this is just the ideal case. So if transformer is 100% efficient, this is the ideal case. Ideal transformer, you can say. Ideal means this type of transformer does not exist in real life. Ideal transformer. So the amount of power you are giving to the input, the amount of power you are giving to the input is equal to the amount of power you will get at output. Input power is equal to output power. Here you are supplying the power, and same power you are getting here, means input power is equal to the output power. And what is the formula of the power? Power is given by EMF, or you can say potential difference into current. EI will be the power. Power is equal to EI. E is the EMF here, I is the current. So input power is given by, this is the input, na? This is the, hello Fawaz.
Hi, sir.
Hello, how are you, Fawaz?
I'm fine. How are you, sir?
I'm good. So today I am discussing the transformer. I think you already know. So just I have told you that this formula, after derivation we will get. What is ES? ES is the induced EMF, or you should write EMF. EMF at secondary coil. EP, EMF at primary. In other words, you can say this is the output voltage. What is this? This is the output voltage, and this is the input voltage, and this is the input voltage. NS, number of turns for secondary coil. NP, number of turns for the primary coil. Okay, this is the secondary coil having turns. This is the primary coil having turns.
Sir, where is EP?
Just a minute. EP. EP is this. This is EP. Okay, so after the class I will explain you. Okay, otherwise there will be the disturbance in the class.
Okay, okay,
Okay,
sir.
because we are having a flow, na. So
Yeah,
we
yes,
are
yes, sir.
moving. We are moving with some flow. No, but no problem. You should remember EP is the primary voltage. EP is the voltage at the primary. Okay, I can write here also. This is EP. This is ES. Now, okay,
Yes,
okay.
yes, sir.
Now focus. Now focus. If I am just assuming this transformer as 100% efficient, means the power you are supplying to this transformer, input power you are supplying to this transformer, same power you will get here if there are no loss of power. So power input is equal to the power output, and power is given by EMF multiplied by the current. So power input means EMF. Okay, so EMF, input EMF, or you can say EMF in primary coil multiplied by current in primary coil. This will be the input power. Output power will be the actually I have written E like this now, so I have to write E like this. This is EP multiplied by IP is equal to ES multiplied by IS. What is EP? Primary voltage multiplied by primary current. Voltage in the primary coil, IP is the current in the primary coil. ES, voltage in the secondary coil. IS, current in the secondary coil. Okay, so you can write from this equation E suffix S is equal to E suffix P is equal to IP is divided by IS. We can write IP divided by IS. We can write. Okay, so this is another formula, but just wait a minute. So this formula we will get this formula, but this formula is valid when your transformer is 100% efficient. This formula is valid for ideal transformer. For transformer, for ideal transformer, this formula is valid, and this formula is valid all time. This formula is valid all time. So from this, you can say that from this formula you can say that EMF in the transformer is inversely proportional to the current in the transformer. Okay, so here we can write, so if we increase voltage, current decreases, current decreases and vice versa. This is the relation. If you will increase the current, EMF will decrease. If you will decrease the current, EMF will increase. If you will increase the EMF, current will decrease. If you will decrease the EMF, current will increase. So basically, you can write. mm, Now you have two relations. One is this, another is this. So for 100% efficient transformer, you can write EMF in the secondary coil divided by EMF in the primary coil is equal to the number of turns in the secondary coil divided by number of turns in the primary coil is equal to the current in the primary coil divided by the current in the secondary coil. So this formula is valid for 100% efficient transformer. 100% efficient transformer, this formula is valid. Okay, so this formula is valid only when the transformer is 100% efficient. But this relation is valid all time. If you want to write this relation or you want to write this, this and this relation, means this relation valid for ideal transformer. Ideal transformer means 100% efficient transformer. Remember, one question, we will do one question. Okay, so here this is a soft iron core. This is a soft iron core and oh, this is a soft iron core, and on this soft iron core winding is there like this. One winding is like this, another on another side winding is like this. Okay, this is the winding condition given. So this is your primary coil, this is your secondary coil. Number of turns in the primary coil is given as 100 and number of turns for the secondary coil is given as 200. Okay, here input means input voltage and input current is given. So input voltage is 220 volt and output voltage input current is 10 ampere. What is the meaning of this? Na? In this primary coil, the current is 10 ampere and the voltage value, peak value of the voltage is 220 volt. We want to find the output. Output means we want the output current in the secondary coil, and we want the voltage in secondary coil or EMF in secondary coil. This we want to find. Okay. Okay, use this formula. First note down. Fawaz. Hello, Fawaz.
Yes, sir.
The,
Yes.
have you completed this diagram yesterday?
Yes, sir.
So
Till this
I think
fair 5B
I think
equals
you should.
B dot A.
Yeah. So I think na,
Yes.
you should you should just write either you if you want to write or because I want that you should solve, you all of three should solve this question by yourself. Okay, and remember this transformer is the ideal transformer. Ideal transformer. Okay, so do one thing, Fawaz, write down from here. Okay, Hamza and Nida, you should also write down from here. Then question, I want that you should solve that question. Okay, so all of you please note down. Hamza, please take the screenshot.
Sir,
Nida,
can I
please
take
write.
screenshot? Or
Of course you can
I
take the
have to note
screenshot.
from little up. Little up.
Hmm. Little up. Okay, okay, so
Yes,
from
up.
here you want na?
Yes, yes. Yes.
Taken.
Sir, I missed the little up part.
Okay, 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 so take this. Now take.
Yes, sir. Yes, sir. Okay.
Taken.
Yes, yes.
Now Nida and Hamza, write down this part. Hello Hamza.
Yes, sir.
Have you taken the screenshot?
No, sir, I'll take at the end.
Okay. So take the, you can take the screenshot of this now. So otherwise, uh, Fawaz, have you completed this part? If you have completed, then I will scroll down. But
Done.
completed, Fawaz? Fawaz completed na?
Yes,
Okay, okay.
yes,
So
done, sir.
okay. Now complete this part. Both of you, three of you, and then first analyze the formulas and try to solve the numerical by yourself. I will also solve the numerical, but I want that you should solve. completed Nida and Fawaz. Okay, Fawaz completed. Scroll down. Should I scroll down?
Yes.
Okay, so now try see this formula. Okay, see this formula. This is valid for ideal transformer, and I have told you all the things. This is IP is the current in the primary, current in the secondary, number of turns in secondary, number of turns in primary, EMF in secondary, or you can say voltage in secondary and voltage in the primary. So here, this is the ideal transformer. Primary coil is this, secondary coil is this. This data is given. This data you have to find. Now, Hamza and Fawaz and Nida try to solve this question and tell me the answer. This is very easy question, very easy question. The ES is 440 and IS is 5. Very good. Right answer. Fawaz and Hamza, what about you?
Yes, same answer.
Hamza? Okay. So now I am solving this question for Hamza. Okay. Very easy question. This formula will be used. Yes. So here, suppose I want to find first IS. I want to find first IS. So I will use this relation. I will use this relation. That is NS by NP is equal to IP by IS. Number of turns in the secondary coil is 200. Number of turns in the primary coil 100. Current in the primary is given as this is IP 10 and what this is IS. Okay, so you will get IS as 5 ampere. 5 ampere. You will cancel this. Cancel this. Now, if you want to find secondary voltage, then either you can use this formula, this and this formula, or you can use simply this ES by EP. ES by EP is equal to NS by NP. What is ES you want to find? What is EP? 220 volt. What is NS? 200. What is this? What is NP? 100. So when you will cancel this out, so finally you will get ESS 440 volts. 440 volts. Hamza, take the screenshot of this question.
Yes, sir.
I will try to send the notes to all of you because I have to arrange the note now, means I have to arrange the slides and all that. So that is why I am not sending.
Sir, can you scroll down?
Yeah. Suppose if I will use send, if I will
Okay, done.
send the, if I am sending the notes and you are just sitting and watching, I am writing and you are just watching like a movie. So if you, I always advise to a student that make your own notes. If you are taking the screenshot, that also will be your notes. So if you will uh, try to write something na, so the learning capacity of your mind becomes double, triple, and 4 times depending upon the person. Okay, so but here na, we have taken a transformer which is 100% efficient, transformer which is 100% efficient, but in real life nothing is 100% efficient. So we will talk about the practical transformer that is used in real life. Practical transformer. Practical transformer. So what happens in practical transformer? Input power is not equal to the output power. Power input is not equal to power output. Why? Because there are some losses. We will discuss some losses. So we say that uh, input power will always be greater than the output power. Okay. This is P in and this is P out. So input power will always be greater than the output power because there will be some loss of power. So you can say that EP IP will always greater than ES EP IP will always greater than ES IS. Okay, now we will talk about the efficiency of the transformer. How efficient the transformer is in real life. Efficiency of transformer. Efficiency. Efficiency is represented by eta. Eta. So efficiency is power output divided by power input. Power output is given by, output power is for the secondary coil. So ESIS divided by EPIP multiplied by 100. So this will be your efficiency of power. Efficiency. Okay. So now this chapter is finished. Write down this. Efficiency means see here. Suppose This is the transformer, na? This is the transformer. Here you have applied the power. You have supplied the input power to this. Input power to this. Suppose 10 kilowatt power you have supplied. Power supplied. So what will happen now? Here there are some losses due to different causes. There will be the losses. One of the losses I am telling, here are the wires, windings. So these windings have some resistance. So due to that, there will be some loss of the power in the form of the heat. So at output, some power is already lost. Some power is already lost. Suppose output power you are getting 8 kilowatt. For example, I am saying you are getting 8 kilowatt. So efficiency means this is will be 8 divided by 10 into 100. So means the efficiency of your transformer will be 80%. 80% efficient this transformer will be. Okay. This is the meaning of the efficiency. Fawaz, got it?
Okay, sir. Thank you.
So write down this. We will discuss after this the losses in the transformer. More the efficiency of the transformer, more the transformer will be more the efficiency of the transformer, more better will be the transformer.
Done, sir.
Nida, complete it, and Hamza, take the screenshot. Last topic of this chapter, Eddie, means losses in the transformer. Losses in the transformer. Last topic we'll discuss. Hamza, taken the screenshot.
Yes, sir, take it.
Okay, okay. Good. So losses in the transformer. Why we are studying the efficiency? Because there are the losses in the transformer. So losses, energy losses in transformer. Energy losses in transformer. So number one, flux leakage. Flux leakage. What is the meaning of the flux leakage? See here, here. Hmm. In the transformer, these are the magnetic field lines. But in actual, the magnetic field lines are not straight lines. Magnetic field lines are curved also. So magnetic flux will be leaked. I'm just drawing here. In actual, what happens? This is your transformer now, and this is the soft iron core of the transformer. So what happens? The magnetic field lines will be like this. Suppose this is the first magnetic field line. I am not able to make straight line. Okay, so this will be the another. This will be the another. So there will be some flux leakage. Means there will be some magnetic field line which is outside of this core. Why? Because in actual magnetic field lines are the curved lines. Okay, So that is the flux leakage, leaking of flux. So how to minimize the flux leakage? How to minimize the flux leakage? If you want to minimize the flux leakage, you have to use soft iron core in the transformer, because soft iron core attracts the magnetic field line, so flux leakage will be reduced. Use soft iron core. Soft iron core. Second is resistance of winding. Resistance of winding, that I have told you. Windings are what? Wire, and wire have some resistance. Wires have some resistance. So there will be the heat loss or energy loss in the form of heat. That energy loss is given by I square resistance of the wires into T. T is the time. If you want to minimize it, so you have to decrease the resistance of the winding. You have to decrease the resistance. You have to decrease the resistance of the winding. For that, what you have to do, you have to use a material or a wire have low resistance like copper. Use copper. But copper is a costly material. Copper is a costly material. We cannot use a copper after a certain limit. Okay, so this will be the solution, but this is not uh, the proper solution, you can say. We should use the copper as minimum as possible. Okay, so instead of that, what we do, uh, we use thick wire. We use thick wires. Why we use thick wires? Because we know that resistance of the wire is equal to rho L by A. Means you can say resistance is inversely proportional to area. If the wire is thick, if the wire is thick, area will be reduced. Oh, sorry, what I am saying. If the wire will be thick, thick means having large diameter. So the area of the wire will increase. If area will increase, then you can say this resistance will decrease. This resistance will decrease. If the resistance is decreasing, then you can say energy loss is decreasing. So basically we use the thick copper wire. Okay, thick copper wire we use, and we cannot use copper after a certain limit because copper is so costly. So what we do, the final solution, you can say, we use thick copper wire. On that side, of transformer, of transformer where the current is high, where the current is high, where the current is high. One more loss is there. hysteresis loss. Hysteresis loss. Okay, so what is hysteresis loss? As in the transformer, there is alternating current, and alternating current changes with time. So due to that, alternating current magnetic field also changes with time. So due to change in the magnetic field, sometimes the magnetic field increases, sometimes the magnetic field will decreases. Means magnetization and demagnetization of the winding takes place. And due to the magnetization and demagnetization of the winding, there are losses known as the losses. There are the losses known as the hysteresis losses. So basically what happens? Alternating current okay, changes with time, changes due to which magnetic field changes. So you can say there is a magnetization and demagnetization. You can say continuous magnetization and demagnetization take place. Hence, energy losses okay, energy losses. So what is the solution? What is the solution of this? We use soft iron. We use soft iron. There is one more loss, that is eddy current loss. So what happens? We know that the current is alternating, so current is changing continuously. Due to that, the magnetic field is changing continuously. Due to that, the magnetic flux changing continuously. Due to that, there will be induced EMF. Here there are two types of induced EMF. So what is happening? Current changing continuously. Due to that, magnetic field changing continuously. Due to that, magnetic flux changing. Due to that, EMF induced. This story I have told you approximately 100 to 200 times. Here in this case, there are two types of induced EMF. One induced EMF will induce across windings. Okay, we have copper windings. copper wires. See the structure of the transformer. Here current changing, magnetic flux changing, EMF is inducing in this winding. First is this, and there is other bulk surface of this, na? This surface, suppose what about this surface? About this surface also, about this piece, you can say, of the transformer, about the part of this transformer, there will be change in the magnetic flux. So here also there is an induced EMF in the bulk of the transformer, and that is responsible for production of or generation of the eddy current. And if the current is generated, heat will produce due to that current. Heat will produces due to that current. So this EMF induced in material of core means two induced EMF are there. One EMF induced in windings, we know. Other induced EMF induces in the material of the transformer itself. Material of core, that is soft iron core. So in soft iron core, in the material of the soft iron core, the EMF induced soft iron core. Okay, so as EMF is induced in the soft iron core, due to that there will be eddy currents. Due to EMF there will be current. There will be eddy currents. There will be eddy currents. So basically eddy currents are like this. Suppose this is the core of the winding. This is the soft iron core, and eddy currents are like this in circular form, like this. These are the eddy currents. I suffix D is the eddy currents. Eddy current. So eddy current losses will be due to these eddy currents. Energy loss is given by ID square resistance of the bulk material into time. This will be the energy loss. R is the core material resistance. Core material resistance. So what is the solution of this? To minimize this, we use laminated cores with insulating liquid in between. We use laminated cores with insulating liquid in between. Okay, write down. So in 2 marks this question can be asked, what are the losses, energy losses in the transformer? So you should have the basic, you should at least have the basic idea. Write down. So from my side, this chapter is finished. Completed? Okay. Fawaz and Hamza completed.
Yes, sir. Done.
Write down. Fawaz and Hamza completed.
Sir, 1 second.
Okay. Now in the next class, we will start the electromagnetic wave. Electromagnetic wave. Okay. Electromagnetic waves we will discuss. That is a small chapter. We will try to finish that chapter in one lecture. Oh, not one, two lectures. After that, we will start the optics.
Sir.
Okay. Completed now? So here now these are circular types of currents generated. These induces, you can say. So these currents are known as the eddy currents. Eddy currents is removed from your syllabus, so that is why I am not telling this in detail. Hamza and Fawaz
Done.
and Nida, scroll down. Okay. Hamza, are you taking the screenshots?
Yes, sir.
Okay. Now after this, I want that you should revise your notes, and I am not saying that you will get 100% of the things that I taught you. At least if you are getting 70%, 80%, 90%, depending upon different person and depending upon your efforts also. So at least main things you should know at least. So I can only show you the path, but you have to travel that path. Okay, I can show you the path, and I can tell you how to handle the difficulties that will be arise in the path. I cannot go with you for that path. Okay, you have to alone go to that path. Again and again I am saying, in physics uh, the concepts are linked with each other, related with each other. If you will skip one class, if you don't know that concept, the next concept, in next concept there will be problem, in next concept there will be problem for you. Okay, all of you, so we will meet in the next class with the next chapter, electromagnetic wave. Okay, we will try to finish that in 2 lectures. Okay, so till then, okay, revise your notes properly, and now we will meet in the next class. Okay, all of you.
Okay.
Okay, thank you.
Okay, fine.
Thank you, sir. Salaam alaikum.
Walaikum assalam.